I want to go back and just make sure that you are really clear on these key parts. So networks and graphs form part of next year. So you have to have this down pat, just like matrices. So just remember what vertices, edges, and isomorphic graphs are. So the points are called the vertices. So each of these dots are vertices. They are connected by edges. So these are the edges that connect those vertices. Um, so it's usually a vertex is labeled by the single capital letter, and then we label the edge by showing the two vertices that it is connecting. So this edge here would be called DC because it connects the vertex D to the vertex C. So we write it DC. If we have graphs that show exactly the same connections, they are isomorphic. So they may look different, but they are displaying the same information. They are isomorphic. Okay, features of a graph. So faces are the enclosed regions of a graph. We have to make sure that we have no edges crossing, and then we need to redraw it if there are edges that are crossing. So this graph has 6 faces. The loop at D, where no edge starts and ends at the same vertex, creates a face. So this loop here. There are 2 multiple edges between A and E that create a face, so in here. And then the region outside also counts as a face. The degree of a vertex is the number of edges connected to that vertex. Remember, Mr. Norman said we draw that circle around it and how many lines are coming out of it. The degree sum of a graph is the sum of its degrees for all of the vertices. So degree sum is 2 times the number of edges. So remember, edges are these lines that connect our vertices. So please make sure you have this information in your notes. Don't rely on just hoping you'll remember. Write it down and do the worked examples. Adjacency matrices. So they are used to, so adjacency matrices used to describe the graphs by showing the number of edges connecting each pair of vertices. So this is the adjacency matrix for this graph. Again, please make sure you just have this information in your notes and you know how to apply it. Down to types of graphs. So we've got a connected graph where all of those vertices are connected. You can travel from any vertex to any other vertex. These are not connected. You cannot travel from this vertex to any other vertex. It is isolated. Planar graphs. They are connected graphs that can be drawn so that no edges are crossing. Okay, so these edges are crossing here, but we can redraw it so that it is planar. Okay, this one can't be redrawn, okay, so that the edges aren't crossing, so it's not a planar graph. All right, Euler's formula. It applies to graphs that are both planar and connected, has to satisfy both those criteria. So the number of vertices plus the number of faces minus the number of edges should equal 2. So again, please make sure you have Euler's formula written down. Please make sure that you have used it and you have some worked examples in your notes about how it operates. So this is very important. You also need to really understand what a vertex is, what a face is, and what an edge is. Okay, subgraph. So subgraph is just a part of the larger graph. It must show the same information. So it cannot add an extra edge, but it can just remove parts of that larger graph. Okay. Again, make sure you understand that. Now we're on to walks and weighted graphs. This is probably one of the more challenging parts that you're going to need to unpack and use. So again, really have these documented in your notes and come up with some way in your mind that you can understand the difference if you haven't got your notes on you. So, graphs can be used to solve traveling and exploring problems. We want to find the shortest route between different locations. So, it's from moving from one vertex to another along an edge. We have to know these definitions. So a walk is a sequence of connected vertices. Okay. In a walk, edges and vertices can be repeated. So a walk has really very few constraints on it. Okay, so we started at A, we went to B, we went to E, we went to C, we went back to E, and then we went to D. So we've traveled along this along this edge twice. Okay. Whereas a trail is a walk, but it has no repeated edges. Okay, so can you see here that we've hit every single vertex? And in a walk, we've repeated this edge. In a trail, we have hit every single vertex, but we cannot repeat the edge. So we couldn't come back along CE because that would have been a repeated edge. So a trail has no repeated edge. But we have visited this vertex twice, okay? So a walk has repeated vertices and repeated edges. A trail has repeated vertices, but no repeated edges. A circuit is a walk that has no repeated edges and must start and finish at the same vertex. So we start at A, we go to B, E, C, D, E, and back to A. So can you see that we can repeat vertices, but we have to start and finish at the same vertex. Now, a path has no repeated vertices. All right. So we've gone from A, B, E, C, D. Okay. So a path is a walk with no repeated vertices. So we didn't come back to E. So can you see that we've got a path and then we've also got a trail. So a path has no repeated edges, but a trail has no repeated edges, but a path has no repeated vertices. A cycle is a walk with no repeated vertices and it starts and finishes at the same vertex. So can you see we've got two that must start and finish at the same vertex, and then the rest can start and finish wherever, but they have some constraints on if we can repeat the vertice or repeat the edge. So please have this in your notes. It is so important that you have this documented. All right. I want you guys to put this up on the screen and I want you to talk yourselves through it. You are going to use this flow chart to decide which criteria they satisfy. All right. Take yourselves through it. Take your time to see if you can unpack it. And then come back and double check your answers. Okay. Weighted graphs and shortest path. So a weighted graph, sometimes called a network, where we have extra information on there, like distances, times, or costs. Okay, so an example of this might be our towns and the roads that connect them. So the towns would be the vertices and the roads are our edges, and we would have the distances on those edges. We use this information to solve a shortest path problem. Okay, so we want to find the shortest distance to get from B to G, for example. There are multiple different ways that we can do it, but we might want to find the shortest path because we haven't got a lot of time to be in the car. All right. Again, take yourselves through the worked example, talk through it, draw it up on the board, and then complete the question. And then I want you to go on and have a go at these questions. You will need to use that flow chart to start you helping understanding whether it's a trail, path, circuit, or cycle, or just a walk. That is probably going to be the most critical part to get your head around and probably the one that will take the longest time. So I need you to do the practice and do the work. We will revisit it next lesson.